Welcome everyone. My today's topic is understanding the ADAM optimization algorithm in machine learning. The purpose and objectives. Our main goal is to explore how the ADAM optimization algorithm works, both in theory and in practice. Also, we want to compare how well the ADAM performs compared to the other advanced methods when applied to common datasets. Additionally, we aim to evaluate how accurately the algorithm can identify and categorize our test dataset. This will help us understand its strengths and possible weaknesses in real-world use. Let's start with what is machine learning. Machine learning and artificial intelligence are significant areas of interest in both contemporary science and society. They represent some of the most advanced technologies applicable across various industries, including healthcare, finance, transportation, and entertainment. The theoretical foundations of machine learning have been explored and expanded upon by some of the greatest figures in the field. For example, Geoffrey Hinton, often referred as a godfather of deep learning, has laid the groundwork for many modern machine learning techniques with his research on neural networks. Jan LeCun's work on convolutional neural networks has revolutionized computer vision and pattern recognition, while Joshua Bengio's uh, contribution to neural network model have greatly advanced natural language processing and unsupervised learning. As we dive into the fundamentals of machine learning, let's start by understanding what a machine learning model is. Essentially, it is a program that learns from data to make predictions or decisions, eliminating the needs for explicit programming for each specific task. There are three primary types of machine learning. Supervised learning, where the model is trained on labeled data. The model learns to map inputs to the correct outputs. Unsupervised learning. In unsupervised learning, the model is trained on unlabeled data and must find hidden patterns within the input data. And reinforcement learning. This model mimics how human learns from experience. The model interacts with the environment, makes decisions, and learns from the consequences. As we continue, it's important to note that our focus will be on neural networks in supervised learning particularly, because we will be discussing the ADAM optimization algorithm, which is widely used in training those types of models. To understand how a neural network functions, we need to understand its basic structure, which can be broken down into several key components. Uh, the input layer. This is the initial layer of the model where the raw data is fed into the system. Each node in this layer represents a feature of the input data. Between the input data and the output layers, we have one or more hidden layers. Uh, these layers perform the core computations and transformations on the input data. The output layer is where the model generates the predictions. The structure of this layer depends on the specific task. Weights and biases are the parameters that the neural network adjusts during training. Optimization is a fundamental aspect of machine learning. When an input signal is received by the model, it undergoes processing through a function, and after a series of computations, it transforms into the output value. Then the model compares the generated output with the actual output value and computes the metric called loss function. The loss function is a measure of how well the model performs on a given task. You can see some of the basic loss functions used in machine learning on this slide, which are mean squared error, or MSE, mean absolute error, or MAE, and binary cross entropy loss. Next, we need to find an optimization algorithm capable of efficiently minimizing the loss function. The effectiveness of an optimization algorithm is crucial because it influences how quickly and accurately the model converges to an optimal solution. To illustrate this, let's look into two graphs. The first graph shows a model with poor accuracy, where there is a significant mismatch between the predictions and the actual value. The second graph shows a model with better accuracy, where the predictions closely match the actual values. To achieve such results, different algorithms are used. Their task is to adjust the model's parameters, specifically weights and biases, so that the model learns to make more accurate predictions. The first algorithm that we'll look into is gradient descent. The idea of gradient descent is to update the parameters of the model by moving in the direction of the steepest descent of the loss function. The gradient descent calculates the derivative of the loss function concerning each model parameter to determine the direction of the update. The algorithm updates the weights by subtracting a fraction of the gradient from the current value of each weight. This fraction is known as the learning rate, denoted by alpha, and it controls the size of the step taken in the direction of the negative gradient. This process is repeated iteratively, and with each iteration, the algorithm progressively approaches a local minimum of the loss function where the weight values are optimal. Standard gradient descent requires computing the gradient of the loss function over the entire dataset, which can be resource intensive, especially with large datasets. Therefore, in such cases, stochastic gradient descent is applied, which is more efficient for optimizing models with large amount of data. Standard gradient descent updates the model weights using the entire dataset. However, stochastic gradient descent computes the gradient and updates the weights for each data sample in the dataset separately. That means that on each iteration, SGD uh, uses only one data sample instead of the entire dataset, allowing for quick weight updates and more efficient processing of large datasets. However, SGD can be sensitive to the initial values of the weights, causing it to get stuck in a local minimum and fail to find the global minimum of the loss function. That's where ADAM comes in handy. It uses the history of previous gradients to adaptively adjust the learning rate for each parameter, helping to overcome the limitations of SGD. ADAM was presented by Daidara Kinema from OpenAI and Jimmy Buff from the University of Toronto in their paper titled ADAM, a Method for Stochastic Optimization. In ADAM, a separate learning rate is maintained for each parameter weight, which is adapted and updated individually. The algorithm selects a smaller learning rate for frequently updated parameters and a larger one for parameters corresponding to rare features. The ADAM algorithm computes the exponential moving average of the gradient, it is called the first moment, and the squared gradient, the second moment, of the weights, where the parameters beta 1 and beta 2 control the smoothing rates of these moving averages. In the context of exponential moving average, as shown in the figure, smoothing occurs by assigning more weight to newer data. Thus, the model responds more to the recent changes in the data than to older values, allowing it to adapt more quickly to any new data trends. The first and the second moments are statistical concepts. In the context of ADAM optimization algorithm, the first moment is used to estimate the mean value of gradients, which can be viewed as the rate of change of model parameters. And the second moment is used to estimate the variance of gradients, reflecting how gradients are spread out around the mean value. The main idea behind using moments in ADAM is to provide the algorithm with additional information about previous weights, updates, and the gradient direction, enabling better control over the optimization process. ADAM's update rule looks like this, like in the slide, where the value m is the first momentum and v is the second. To measure the effectiveness and universality of the ADAM, we compared it with other optimization algorithms on two datasets, MNIST and FashionMNIST. We chose them because they are often used as a benchmark for testing new machine learning algorithms and models. MNIST is a classic dataset consisting of black and white handwritten digits. FashionMNIST is another popular image dataset. The images represent various types of clothing items such as t-shirts, dresses, trousers, etc. FashionMNIST consists of more complicated pictures than MNIST, and by evaluating ADAM's performance on these diverse datasets, we can see how well it works across different types of data, showing its usefulness in various situations. On this slide, the first figure illustrates the training process of models on MNIST dataset using various optimization algorithms. The results indicate that despite the task not being very complicated, Adam successfully demonstrated the best performance among all the algorithms with the accuracy around 97.63%. The second figure illustrates the training process of models on FashionMNIST dataset. Despite more complexity, Adam managed to outperform other algorithms. The accuracy the model reached is around 90.56%. To make sure our model works well for our specific needs, we made a small dataset ourselves. The famous MNIST dataset created by American researchers might not catch our handwritten numbers perfectly, so we wanted to see if our model could still understand and categorize our handwritten characters correctly. This way, we could check if our model is flexible and reliable for our purposes and not just for standard datasets. Uh, the test consists the test dataset consists of 100 hidden numbers from 0 to 9. The results appear promising, with the model achieving the accuracy of 97%, meaning it correctly predicted 97 out of 100 images, which is a very good result considering the model accuracy on a MNIST dataset was 97.63%. In conclusion, we can say that first, the ADAM algorithm is an effective optimization method that combines ideas from other algorithms such as Hermes-Prop and Adagrad. Experiments on various datasets, such as MNIST and FashionList, show that the ADAM algorithm is capable of achieving good results across a wide range of machine learning tasks, and that the ADAM algorithm is effective for optimizing tasks involving both large and small datasets, as demonstrated by experimental results.